This is a 3D printed star tracker. These are 3D printed mounting systems for my camera lenses. This is a 3D printed Bahtinov mask for focusing. This is a 3D printed cable organizer designed for Astro cameras. This is a 3D printed guide scope. And this is a 3D printed go-to mount with auto polar alignment. More and more of the gear that we use to take Astro photos can now be 3D printed. In this video, I'll cover what is happening in the world of 3D printed Astro gear and try some of it out, and of course, show you the results. Hi, my name is Nico Carver. I am a full-time astrophotographer, thanks to the community support here on YouTube, but especially on my Patreon, which starts at just $1 per month. All of the 3D printed items in this video were either printed by me or sent to me for review by their designers. Something I find interesting is the previous time that I talked extensively about 3D printing was in the third video that I made on this channel, which was 7 years ago now. And in that one, I was talking about Bahtinov masks. I rewatched that video, and while most of it holds up, there are a few updates that I'll make in this video later on. Actually, just one update about how to design the 3D printed mask on your computer. So 3D printing isn't new. It was already fairly commonplace 7 years ago when I made that video. But in the past 7 years, the kinds of projects that people are 3D printing have gotten more and more ambitious to the point that we are at now, where people are making all kinds of stuff from mounts to telescopes really successfully. So in this video, I'm going to talk about what 3D printing is, some easy ways to get started in 3D printing, and then I'll review some of the 3D printed gear that is available today and is sold online. Some of these projects are open source, and so that means they'll give you the print files. You can print them out yourself or modify them if you want, while others, they don't sell the print file, just the 3D printed part. But often with those parts fill a specific niche in the hobby where what they're making is the only option, or at least the best available option, to buy off the shelf. So let's start briefly with what 3D printing is. 3D printing typically starts with designing something on the computer in 3 dimensions, of course, using any CAD software. And CAD stands for computer-aided design. That's sort of the category of software, though, for doing 3D work. Some good free CAD software is Tinkercad, which is a simple web-based one, and Autodesk Fusion, which is more full-featured. It's only free, though, if you're using it for personal projects. After you have your 3D model designed, you'll use something called slicing software to convert your 3D model into instructions that the 3D printer understands. And most 3D printers will either come with their own slicing software or at least have a suggestion for what slicing software to use with that printer. And the reason it's called slicing software is because that is literally what it does to your 3D model. It slices it into many thin slices in the order that the 3D printer will print them out. And now we turn to the 3D printer itself. If you think of a regular printer, the consumables that you feed into it are like the ink and the paper, of course. With a 3D printer, the consumable is filament. It's a thin strand of material spooled onto a reel. And typically, the filament is plastic or a mix of plastic with something else like carbon fiber. There are 3D printers that can print other things like metal 3D printers or even food 3D printers. But in this video, when I say 3D printing, I'm talking about plastic, which is what most people do, especially home 3D printers. So after you have this plastic filament, you typically then dry it out with a filament dryer and then feed this filament into the printer through a tube. The printer then heats the filament up, melting it. This is done with a part called the hot end. And then the melted filament comes out of a nozzle and is laid out methodically according to your model onto a plate in many, many thin layers until the whole part is printed, which can take anywhere from like 20 minutes to hours and hours. 3D printing is also called additive manufacturing because you build the part by adding one thin layer after another rather than all at once like you could with injecting plastic into a mold. While something simple like a Bahtinov mask, which was what I would typically print, you can just design the mask, send it to the printer through the slicing software, and about 30 minutes later, you have your finished mask. It's probably going to work out fine. So the whole process with something like that is really simple and straightforward. The only times I've run into problems with something like printing a Bahtinov mask is if I made a mistake measuring it, measuring the lens or something. But a mask is simple. Something like a tracking mount or a guide scope is going to be made up of several 3D printed parts, and they all have to fit together really nicely for the whole thing to work. So my first suggestion, if you want to start learning 3D printing, is start with like a few simpler projects, like a Badenov mask or maybe like a little bracket or something, projects that are just 1 or 2 parts. And then after you have a feel for how the process works, you can delve into more and more complex projects. My second suggestion to get started is before you go out and buy a 3D printer, first consider finding a place where you may have access to use a 3D printer. In every place I've lived in before this place, I have had public libraries near me that have 3D printers where you can just bring in your models on a flash drive and for either free or a nominal cost, print your model out. Where I live now, it's pretty rural, so I haven't found a public library that has a 3D printer, but I did find a community makerspace about half an hour away that I joined, and as part of my membership fee, I'm able to get trained on and use a number of different 3D printers. Okay, so I've mentioned a number of times that I think a good first project for 3D printing is designing and printing a Badenov mask, which is useful for manually focusing your telescope or lens super accurately. I do have a full-length video on Badenov masks that is almost all good information, but the one part of that video that is out of date is how to actually make the custom 3D print file for your specific lens or telescope. One of the web tools that I was using in the video doesn't exist anymore, at least in that form. But there are some replacement tools that have come out, and the one that I'm going to show you now is really great because it has a 3D output mode. So there's no need to go from a 2D SVG, import that into Tinkercad and all that stuff anymore. It makes the whole process much simpler. So let me quickly show you how this new tool works. The first thing is you should measure the diameter of the lens hood or the dew shield that this mask is going to fit onto. I would then add 2 meters to that measurement and put that in as your mask diameter. So the diameter of your lens hood plus a few millimeters. And it's always better to have that a little loose because it's much easier to then remove the mask without disturbing anything. You don't want it tight. All of these other things you can probably leave alone, but this is now generating a 2D mask. So what we want to do is go up here to the output type, change it to 3D, and you could see the default is this style of mask where it has this little lip and it would sort of just sit a little bit on whatever you're putting it on. I prefer a thicker collar, and a collar does take more filament, but for me, a Badenov mask with a collar is easier to use. So to make a collar, just change the flange height here to something like 20 millimeters. And there you go, that's it. Now you can just click download STL, open that in the slicing software for your printer, and print it out. Okay, so now let's turn to some 3D printed gear you can buy online and what these different things do. So I'll go from small to big. The first thing, which is small but very handy, are these 3D printed cable organizers that slide right onto your Astro camera of choice or ASI Air, and they can be a really big help with cleaning up cable mess. And that helps with keeping cables from snagging on your mount, disconnecting devices, big disaster. The ones I have here are from Smart Components on Etsy, and I'll put the link in the description. He sells them for all the popular camera brands, QHY, ZWO, TubeTech, at very reasonable prices. And then next up, we have mounting systems for camera lenses. And the idea here is that we often want to use lenses for deep sky astrophotography, but there's no easy way to attach a Vixen dovetail, attach a guide scope, attach an autofocuser to a camera lens until now, because these systems handle all of that. This one is the HyperPod, or for the Rokinon 135. It's available from Thinkable Creations on Etsy. It works very well. You can get it in a basic configuration or with the autofocus bracket and gears. These two are custom sets for my Canon 200mm and my Canon 800mm telephoto primes. And these are from NR Stellar at nrstellar.com. And the cool thing about NR Stellar is he allows you to measure any lens and then will create rings, accessory rails, risers, autofocus gears to match your lens perfectly, just with a few measurements you do with the calipers. And you can customize it to include any of these parts you want. With any of these 3D printed lens mounting systems, you'll also want to get a metal universal Vixen dovetail to attach it to, which will then be the attachment point for your mount, the part that actually slides into the saddle. A number of makers make these for not too much. The last thing about NR Stellar is that several of the parts are also available on Agena Astro if you prefer ordering there. I'll also say generally the two places that I go most often to look for these smaller kind of 3D printed parts for Astro are Etsy and Agena. In addition to Interstellar, Agena also carries Buckeye Stargazer, and I've ordered several brackets and things from him. Okay, moving up in size, this is a 3D printed guide scope called the Open Astro Guider. As the name suggests, this is open source, an open source design, so you can try printing it out yourself and making it yourself. But the designer Fabian also made it available fully printed and assembled from his Open Astro Tech website. And so on there, you can see there's an option for an internal dew heater or no dew heater. And the internal dew heater is just one example of many ways that Open Astro Tech are innovating. I've never had a guide scope with an internal dew heater, even though once I heard that this had it, it seemed really obvious. Like, why wouldn't more have that? It's really cool. The guide scope also has the guide camera sensor built into it, which is a mono IMX290, one of my favorite sensors for guiding. So when you consider this is a 50mm guide scope with a dew heater and the camera sensor built in, the price of 98 euros or about 112 US dollars is incredible. The cheapest guide setup from a big brand like ZWO with a mini guide scope, the guide camera, and the dew heater is going to be 3 times that easily. Okay, and so very impressed by this. It works. The next biggest thing I have here is the OG Star Tracker. This is version 2 by Andrei Gezdesh. I previously reviewed version 1, which I was already impressed by, to get a very accurate belt-driven star tracker. It was really cool. Version 2 improves on the first one, mostly by making it more portable. The first one didn't pack down easily, while this one is much more easy to collapse the latitude adjuster base here, making it a bit smaller. The plan to make this tracker yourself is also available for free if you want to try 3D printing it. I did not 3D print it, but I did ask Andre to send me it as a kit so I could put it together myself, which I enjoyed doing, not only because I find stuff like that fun, but also because it helped me understand how the tracker works a lot better and what went into its design. Okay, and in addition to the physical tracker, Andre and his collaborators have been working on improving the software that works with this tracker, which is a web interface. So this tracker creates its own Wi-Fi network, and then you connect to the Wi-Fi network and go to a web interface in your browser on your mobile device, and that's how you control it. And it allows for, turning the tracking on and off, manual go-to, some other cool options, slewing. And then if you attach your DSLR or mirrorless camera to the mount, and then you have this little cable, you can then use the mobile web interface as an intervalometer, but it's better than a standard intervalometer because it supports dithering. It can talk to the mount as well, which will reduce pattern noise when you stack your pictures. The OG Star Tracker version 2 is available from Andre's website, which is where you'll also find the link for the print files, which are hosted on Printables. Andre also now has distributors in several countries. Here in the US, the OG Star Tracker V2 is available fully assembled from Astro World telescopes for $250, which, if you consider the Star Adventure 2i Star Tracker is $400, I think this is a very reasonable price. Okay, and next up in size, we have the Open Astro Explorer. This is from the same designer as the Open Astro Guider, which we were just talking about. This is a full go-to equatorial mount that you need to connect to a computer in order to use it. And at the moment, to get the most out of this mount, it really should be a Windows PC with Nina installed. And the reason for that is, in addition to being a full go-to mount, the Open Astro Explorer also has a motorized base for automated polar alignment. But that auto polar alignment, at the moment at least, is only working well with Nina's 3-point polar alignment plugin. So you need both the software that goes with this and Nina and that plugin. The Open Astro Explorer is something that you could try printing and making yourself. Fabian sells the electronics and hardware for about 250 euros. He also sells it as a kit with all of that plus all the 3D printed parts for 350 euros. At the moment, the fully assembled Open Astro Explorer is not an option, but if interested, there is a page for adding your email if that does become available in the future. Okay, so the Open Astro Explorer is the biggest 3D printed Astro gear that I have here. But in preparing this video, I was seriously considering trying to 3D print an imaging Newtonian, a telescope. I never found the time to devote to such a big project, but if you're interested in what that would involve and the kinds of pictures you can get, I'd highly recommend checking out Dave Aldrich's channel. I'll link 2 videos in the description. He has a long one about designing and building his DBS 150, which is what he calls his design for his imaging Newtonian, and then a follow-up about various improvements that he's made to it. If you've watched this far, I'd say there's a pretty good chance that you like math. I remember as a kid, I really liked math, but at a certain point in my education, I just sort of lost interest. I don't know if it was the teacher or what it was, but I never took like super advanced mathematics. I only got as far as pre-calculus. But if Brilliant had been around back then, maybe I had taken a different path. Brilliant is the sponsor of today's video, and they have a lot of new features that will help K through 12 and college students really excel in learning math and computer science. The biggest change is Koji, which is their AI assistant. But this AI is different. It doesn't give kids the answers. So it's not about just like asking ChatGPT for the answers and you plug it into the assignment. Instead, it's a one-on-one tutor that helps students think through problems on their own. And it's with them the whole time in a fully interactive way. It's not just the chat. Koji can also actually interact with the student on the visual problem itself. It like moves around the screen. I really wish I had something like this when I was in high school. It may have been what I needed to go on to calculus and beyond. So if you're a parent looking to give your kid, a better way to learn, click the link below or scan the QR code to get started with Brilliant's Tutor for free. You can upgrade to Premium to unlock all courses. And right now, Nebula Photos viewers can save 20% off an annual subscription at brilliant.org/nebulaphotos. Okay, now I want to turn to what it was like to actually use all of this 3D printed gear and what kind of results I got. So let's start with the OG Star Tracker V2. The OG Star Tracker V2 is dead simple to use in a basic way. So if you've ever used a Star Tracker before, it's just polar align it. I use the green laser option. There's also a polar scope option. You point your camera with the ball head at whatever you want to shoot, plug in power, which is just USB-C and can be, just a simple battery bank. And then you start taking pictures. And as someone who's been doing this for years with the green laser polar alignment, I can set up this tracker and be imaging in literally 2 minutes. If you're brand new to this, it will of course take longer to get used to everything, but I really like Star Trackers as a first setup for beginners. I already went through all my reasons why in the first video where I was comparing this to smart scopes. But to reiterate, if you're coming to Astro from photography, I think this makes perfect sense because you already know your camera. It would just be adding one Astro-specific thing, and this one's only $250, so it doesn't break the bank. $250, that's cheaper than any smart scope even. So once you get used to its basic functionality, which is just star tracking, which of course it does very well, you can then try the mobile web interface, and you can use that without attaching your camera, but to get the most out of it, you'll want to attach your camera. For that, you just need this cable, which is like an intervalometer cable. You can get these on Amazon. The port on the OG Star Tracker is 2.5 millimeters. On my camera, that one's port is also 2.5, so this one's just a 2.5 to 2.5. Your port might be different. Once you have that all connected, it's pretty straightforward to trigger the camera and dither between exposures, which, as I mentioned, can reduce pattern noise once you stack. Something new in the software is manual go-to. To get the most out of that feature, you'll also want to get a Skywatcher declination bracket and the manual go-to upgrade from the OG StarTech website. So that adds about $75 total. They have instructions for how all that works. I've tried this with a variety of lenses. I found up to 300 millimeters was doable, like my Tear 3S, as long as they kept the exposure length reasonable, like 30, 45 seconds, something like that. My favorite lens, though, to use with this Star Tracker or any Star Tracker is my Canon RF85 1.2, which, as you can see here, is a pretty chunky lens. It's 2.5 pounds or 1.2 kilograms. But with a Star Tracker at 85 millimeters, you can expect to keep basically every sub. As long as your polar alignment is good, you don't bump the mount, I've just found you can just keep everything, and I like that. And here's an example of a photo I took with the Canon RA, the 85mm lens, and the OG Star Tracker V2. For this one, I combined no filter results with results I took using a clip-in 12nm HA filter to show the extent of just how much AA emission is in Cygnus, which is pretty incredible. And like I said, at 85mm, no subs were wasted. Every single one was a keeper, so I was able to keep hours just in one night. Okay, so now let's turn to this rig that I have here. This is the Open Astro Explorer mount with the NR Stellar ring kit on my Canon 200mm lens. And on top of the Interstellar ring kit is the Open Astro guider. Back here, I have a filter drawer, an ASI 2600 MC Pro, and the cable organizers from Smart Components. All of this stuff is then going to be attached to my Windows laptop, and on there I have installed at least, I think, 5 things to make all of this work. The ZWO drivers, Nina, which is a free program for controlling all your Astro gear, a Nina plugin called 3-point polar alignment, PhD2, which is for controlling the guiding with the Open Astro Guider, and OAT Control, which is the driver and control software for the Open Astro Explorer. And so if you're new to astrophotography, I would say this is going to take several nights to get the hang of using all of this software packages, getting it all to work, configuring all the settings, getting it all to behave as you want. Open Astrotech does have a lot of instructions. They have an English wiki, which I found very helpful, as it has many instructions with screenshots for getting everything set up and working. Just take your time with it though. I will do a quick overview right now and a couple gotchas that I ran into. Okay, so the first thing is you need to know which COM port the mount is using on your computer. Easiest way to do that is open up Device Manager, twirl open the COM ports, then connect the power and USB cables to the mount, connect the other end of the USB cable to your laptop, and then you should see a new COM port appear, a pop-up right there in the Device Manager. And note down this number. This is the mount's COM port number. So then I'm going to open up OAT control software. I'm going to go through the ASCOM setup so that we can also connect the mount to Nina at the same time. So you click on ASCOM setup, you're going to connect to the COM port here in this screen, and then keep clicking next and to connect it fully in OAT control. Okay, and then with that done, we can open up Nina, N-I-N-A, and connect to the ASI 2600 MC camera. That should be connected to your computer, then connect to the mount. I would then start by going to the imaging tab and taking a test photo, making sure you're in focus. If you're not, go ahead and focus. Okay, and then we're ready for automated polar alignment, but there's just a few things that you're gonna have to do, because there's 2 different places for settings you have to look at. The first place is in Nina under plugins. So if you haven't already installed the 3-point polar alignment plugin, you need to install it. And then in that plugin's settings, for me at least, log polar alignment error adjustments, was set to off by default. But this needs to be on for the auto PA to work. The second thing was when I first tried using the auto PA, it would send corrections in the altitude that would actually make the polar alignment error worse, not better. So that was concerning, but it was actually a very easy fix. If the first time you try auto PA, you're seeing either the altitude or the azimuth getting worse rather than better, you need to go into the auto PA settings in OAT control and invert corrections on that axis. So for me, it was altitude, so I said invert corrections on altitude. Once you switch that, then for me at least, and I think this is what Fabian told me as well, it should work every time after you switch it the first time. But this is just sort of like a first setup kind of thing, is you might have to invert the corrections. And then this is what it looks like in action. It automatically moves the mount to different positions in right ascension. It takes pictures, it calculates the polar alignment error, and then the motors kick in and it corrects the polar alignment error all by itself, trying to get those numbers down to 0. I've found once it gets down to under 30 arc seconds of total error, that's good enough. I just stop the process rather than keep it going. Because if you keep it going, it's just gonna keep hunting, but it will just sort of loop overshooting one way or the other. So once you get it down to a reasonable polar alignment error, you can just hit stop. And then with your polar alignment done, you can just set up the auto guider, which pretty much works just like any other auto guider. There are instructions for setting up the driver on the wiki. But in terms of guiding and mount performance, I found on a good night, I could get down to around 0.7, 0.8 arc seconds total RMS. On most nights, it was closer to 1 arc second total RMS. And this should be perfectly acceptable for any wide field instrument, any telephoto lens under 400 millimeter focal length, any one of those many 50 or 60 or 70 millimeter refractors. Those are all going to work great on this. Basically anything that works on the Star Adventure GTI, I'd also recommend for the Open Astro Explorer, and I've made many videos on that. A few other quick things about this mount: it does not come with counterweights. What it comes with are 3D printed inserts for adapting barbell weights to use as counterweights, which is a really cool idea. I just went to Walmart, I think, and got a couple of these little 2.5 pound weights, and then just used the right insert to fit it onto this rail, and it works really well. Something I don't like as much about this mount is balancing it or transporting it for safely, because you have to remove this whole belt and these two 3D printed wings that form the track that the belt moves around. I think that is an innovative design, I get it, but in terms of practicality, I think it's just a little bit too fiddly and annoying to have to mess with that every night at the beginning of my imaging session. Of course, if you don't plan to travel with the mount, you could just keep this fully assembled, just cover it. And so for me, it wasn't really an issue as someone who mostly images from my backyard, which I'm in right now. But if I was considering a mount for travel as a total klutz, which I am, I probably would prefer one that doesn't require as much disassembly and assembly as this one does. So I've taken a lot of test images with this over the past few months that I've had it, but I'll show my most recent one, which is a zoomed in version of what we saw before with the 85mm. And again, I combined narrowband filtered results with no filtered results to get the best of both worlds. This is of course the North America and Pelican nebulae. I've shot this region so many times that I always try to do something a little bit different with it. And so here I thought this rotation was sort of cool with Deneb over here and this feature down here sort of acting as a chin or a smile, and then maybe this whole thing is like a face. I don't know if I'm reaching. I'm always seeing stuff in nebulae. But again, all of the 3D printed gear worked very well here. So I hope this was useful as an overview of some of the 3D printed gear options available now. Definitely a space to continue to keep an eye on, and let me know what I missed and what kind of 3D print projects for Astro that you're working on. And since this video is over 20 minutes long, you're now seeing the names of everyone who supports this channel on patreon.com/nebulaphotos. Patreon members get a bunch of exclusive benefits like monthly bonus videos, one-on-one messaging support with me, tons of additional channels on my Discord server, including the monthly imaging challenge. You also get a Zoom call every month with the whole Patreon community. That's the first Sunday of every month. We call it the Nebula Photos Sunday Chat. And this is just a list of the benefits that everyone gets starting at just $1 a month. There are additional benefits at higher tiers. So I think it would be something that you might want to check out if you appreciate what I'm offering on this YouTube channel through all of the different videos. So that's it for this one. This has been Nico Carver, and I wish everyone clear skies this summer.